A maintenance worker crawls into a steel cylinder 300 feet long. The rotary cement kiln has been shut down for routine repairs. Standard procedure. He's carrying tools, refractory cement, fire brick. The air inside is thick, stifling, still radiating heat from the last firing. He moves deeper into the tunnel. Behind him, somewhere in the control room, an automated system malfunctions. The kiln activates, the doors seal, heat starts building. He's trapped inside a cylinder becoming an oven. Temperature climbing, doors locked, no manual override. He dies from hyperthermia, cooked alive inside the machine he was trying to fix. The investigation finds 6 willful violations and 21 serious violations. Failure to implement confined space procedures, failure to implement lockout-tagout. The company pays over $500,000 in fines. And here's what should terrify you. That wasn't 1890, that was modern times with OSHA, with regulations, with everything the early operators didn't have. This is the rotary cement kiln, a steel cylinder the length of a city block that spins at temperatures hot enough to melt iron. Inside, where the fire burns hottest, it reaches 2,600 degrees. It didn't just make cement, it made the modern world possible. Every skyscraper, every bridge, every mile of highway, none of it exists without this machine. But here's the thing. It's been killing workers the same way for 135 years, and not a single engineer on this planet has figured out how to replace it. In the 1880s, America had a cement crisis. The country was exploding, railroads pushing west, cities climbing upward, bridges spanning rivers that had never been crossed. All of it needed cement, but American manufacturers couldn't keep up. They were using vertical shaft kilns. Load material in, fire it up, wait for it to cool, empty it out, start over. The whole process wasted fuel, wasted time, required armies of workers. In Europe, where labor was cheap, shaft kilns worked fine, but in America, the economics were brutal. It cost more to make cement than to import it. The problem was simple. You needed continuous production. A kiln that never stopped, never cooled down, never required manual unloading. You needed to transform cement making from a batch process into an industrial conveyor belt. But no one had ever built such a thing because the chemistry was unforgiving. You had to heat limestone and clay to 1,450 degrees Celsius, hot enough to partially melt the material and fuse it into clinker. At that temperature, brick crumbled, metal warped, and you had to maintain that inferno while somehow moving material through the system without stopping. In 1877, an English engineer filed a patent for a rotating cylindrical furnace. Brilliant concept. One problem, he never built it. 8 years later, another Englishman decided to try. Frederick Ransom came from a family of heavy engineers. He understood industrial scale. His first experimental kilns were small, 18 inches in diameter, 15 feet long. He set them up in England and lit the fire, and they failed. The fire brick lining couldn't handle the stress. Brick is brittle. Heat it to over 1,000 degrees on one side while the other side stays relatively cool and it cracks. Rotate it constantly with abrasive material grinding against it and it disintegrates. The flame wasn't hot enough. Ransom was using producer gas, cheap fuel made from coal, but it burned cool. It couldn't reach the temperatures needed to properly fuse clinker. The material came out underburned, worthless. Then material started forming rings inside the rotating cylinder, choking off flow. Blockages, jams, complete stoppages. By the late 1880s, Ransom's kilns were considered failures. The whole idea was dead. But in early 1888, a young American visited Ransom's plant. His name was Alonzo Navarro. His father ran a cement operation in New York. What Alonzo saw that day convinced him the technology could work. His father bought the American rights to a patent that had failed in England. The Navarros weren't just buying a patent. They were betting everything on a machine that no one in the world had successfully operated at commercial scale. Think about what that meant in 1889. There were no venture capital safety nets, no government bailouts, no second chances. If the kiln didn't work, the family was finished, but the alternative was worse. American labor costs were climbing every year. European cement was flooding the market. The shaft kilns were bleeding money. They needed a way to produce cement faster, cheaper, with fewer men. The rotary kiln, broken as it was in England, was the only technology that could do it. In July 1889, they set up Keystone Portland Cement in Copley, Pennsylvania. They built a rotary kiln exactly to Ransom's specifications, the same design that had failed in England. In November, they lit the fire. The first burn was rough. Oil pressure uneven. Flames surged and dropped. Material clumped at the bottom instead of tumbling smoothly. The rotation speed was wrong, too fast, and the raw material flew against the walls. Too slow, and it piled up, blocking flow. Nothing worked at first. The material came out wrong. Temperatures fluctuated wildly. The clinker was inconsistent. Well, you couldn't sell inconsistent cement. One bad batch mixed into concrete, and the whole structure was compromised. Every morning they changed something. The mix ratio, the oil injection angle, the rotation speed. They were flying blind. No instruments worth trusting, no established procedures, no one in the world who had done this successfully. December, January, February. The kiln ran. They adjusted, it ran again, more adjustments. By spring of 1890, something clicked. The kiln was producing 125 barrels of cement per day continuously without stopping. It was the first commercially successful rotary kiln in the world, but it was the exact same design that had failed in England. So what changed? The British used producer gas. The Americans had access to oil, abundant, cheap Pennsylvania oil. Oil burned hotter, hot enough to reach proper clinkering temperatures. But there was something else, something the Americans were doing that Ransom hadn't figured out, a technique for protecting the refractory lining. But first, you need to understand what they were protecting it from. Picture a steel tube 6 feet across, 60 feet long, tilted at a shallow angle. Wrap it in massive steel rings and set those rings on rollers so the whole cylinder can rotate. One full turn every 2 minutes. But here's what that actually required. 1,000 tons rotating continuously. The weight had to be distributed perfectly across those support rollers, not approximately, perfectly. Because if the cylinder shifted even slightly off center, the whole thing would vibrate, then wobble, then tear itself apart at the joints. The thrust bearings that kept it aligned had to be checked constantly, greased by hand, adjusted by feel. A man would put his hand on the bearing housing and listen, feel the vibration through his palm, judge whether the alignment was holding. 1 degree off, that's all it took. 1 degree of drift and 1,000 tons of rotating steel started destroying itself from the inside. Line the inside with fire brick. Special refractory brick designed for extreme heat. Seal both ends. Feed raw material into the top. Inject fuel and air at the bottom, light it as the cylinder rotates. Material tumbles slowly downhill toward the flame. It dries, it heats. At 900 degrees Celsius, the limestone breaks down chemically, releasing carbon dioxide. By the time it reaches the bottom, it's partially melting, calcium and silica fusing into hard nodules. Clinker drops out, you feed more material in. The process never stops. Sounds simple, but inside that cylinder, the limestone is undergoing a chemical war. Calcium carbonate is breaking apart at the molecular level. The reaction is endothermic. It absorbs heat, which means the flame has to be hot enough not just to heat the material, but to drive an energy-hungry chemical reaction while doing it. Then the temperature climbs further. The calcium oxide meets the silica from the clay. They begin to fuse. New mineral compounds form. Tricalcium silicate, decalcium silicate, these are the compounds that give cement its strength, but they only form at 1,450 degrees Celsius, not 100 degrees cooler, not 50 degrees warmer. The window is narrow, too cold, and the material stays inert powder, too hot, and it melts into useless slag. You have to hit that window inside a rotating cylinder with material constantly moving. That's threading a needle inside a furnace. At that temperature, you're not just heating material. You're destroying everything the heat touches. The fire brick has to handle a 1,000-degree temperature drop from its hot face to its cold face. That thermal gradient creates expansion on one side, contraction on the other. Cracks form. The raw material sliding through is abrasive. It grinds against the brick like sandpaper, you hour after hour, wearing it down. Then there are the chemicals, alkalis, sulfur compounds. At high temperatures, they attack the refractory, eating into it, corroding it from the inside. And when the refractory fails, when it cracks or wears through, the steel shell underneath is exposed to that inferno. Steel at 350 degrees weakens. At 600 degrees, it glows red. Above that, it warps. You're watching the kiln rotate when you see it, a red spot on the steel shell, not a reflection. The metal itself is glowing. That's refractory failure. Shut down now and you lose days of production. While the kiln cools, men go inside to patch the damage, and the whole system heats back up. Keep running, and the shell warps so badly you'll need to replace an entire section. In 1895, Edward Hurry and H.J. Seamen were running kilns that were eating through refractory faster than they could replace it. Standard problem. Everyone had it. They tried something radical. Instead of just using ordinary fire brick, they coated it with a layer of fused cement clinker. The clinker formed a hard protective shell that resisted chemical attack and abrasion. The refractory brick was failing on three fronts simultaneously. The thermal cycling was cracking it, the grinding material was wearing it down physically, and the chemical compounds in the raw mix were dissolving it from within. Each problem alone was manageable. All three together were destroying linings in weeks. Think about what that meant operationally. You'd fire up a kiln, run it for 2 weeks, maybe 3 if you were lucky, then a red spot would appear on the shell. Refractory failure. You'd shut down, wait for it to cool for days, send men inside to chip out the damaged brick, lay new brick, seal it, heat it back up slowly, or the thermal shock would crack the new lining, and then you'd run for another 2 weeks. The cost was staggering. Not just the brick itself, but the downtime. Every day the kiln sat idle was a day you weren't producing. The clinker coating addressed 2 of those 3 problems in one stroke. It was chemically inert to the same compounds attacking the brick beneath it, and it was harder than the fire brick it protected. The lining lasted longer, long enough to make the operation profitable, but that same year, they made another change. They switched from oil to pulverized coal. Coal was cheaper, more abundant, and when you ground it into powder and blew it into the kiln with air, it burned hotter. The flame was longer. The cement industry pioneered pulverized coal firing, revolutionary. But here's what the patent applications didn't mention. They just introduced an invisible killer into every kiln in America. Finely ground coal suspended in air. That's not just fuel, that's a bomb waiting for a spark. Grind any solid fuel fine enough, suspended in air at the right concentration, and you've created an explosive mixture. All it needs is ignition. And every kiln startup was an ignition event. Remember those ring formations that plagued Ransom's kilns? They never went away. Material fused to the cylinder walls, built up in thick bands, narrowed the opening until the kiln choked. Operators had to break them using long iron rods pushed through access ports while the kiln was still running, while it was still hot, while coal dust hung in the air around them. One spark from an iron rod striking fused clinker. That's all it took. Lighting a rotary kiln isn't simple. You're dealing with a 60-foot cylinder that's been cooling overnight, still warm inside. Too warm to enter safely, but cool enough that the refractory is contracting, potentially cracking. You need to heat it back up slowly, or the thermal shock will destroy the lining. So you start the burner, inject pulverized coal and air through a long pipe at the bottom end, ignite it with a torch on a rod from a distance. If you've purged the air properly, if the fuel-to-air mixture is right, the coal ignites smoothly. But if gas or coal dust has been sitting in the kiln mixing with oxygen, if the purge wasn't complete, then when you light that torch, the whole mixture detonates. Well, the fireball doesn't just burn, it expands violently, and the path of least resistance is straight back through the access door into the face of whoever's holding the torch. A kiln technician was performing a routine startup, standard procedure. He'd done it before. First attempt didn't take, the flames sputtered out, he prepared to try again. What no one had checked, gas remained in the kiln from the failed attempt. It hadn't been purged. On the second lighting, the gas ignited all at once. Fire blew back through the access door, the kind of explosion that doesn't just singe. It cooks tissue deep beneath the skin. He died 3 weeks later. The investigation found he hadn't been properly trained. The gas hadn't been purged, he wasn't wearing adequate protection, there were no written procedures, that wasn't the 1890s. That was modern times, with safety regulations, with OSHA, and it still happened. So what chance did they have in 1895, when no one understood explosive fuel-air mixtures, when there were no purging procedures, when safety equipment meant whatever a man could improvise, how many were burned by blowback, how many died? We don't know because no one was counting, but explosions weren't even the worst part. The worst part was what happened when something went wrong and you were already inside. The kiln has been shut down for refractory repair. It's been cooling for hours, but cooling is relative. The bricks have been holding 1,450 degrees. Even after hours, they're radiating heat. The air inside is thick, stifling, barely breathable, and it's not just hot. As the kiln cools, the chemistry changes. Carbon monoxide builds up in the dead air inside the cylinder. Invisible. Odorless. A man breathing that air doesn't feel sick at first. He just gets dizzy, sluggish. Then his legs go weak. Then he can't think clearly enough to realize what's happening to him. Carbon monoxide poisoning doesn't feel like poisoning. It feels like exhaustion. But the lining has failed, that there's a crack, a whole section is worn away. And if you don't fix it before the next firing, the steel shell will be exposed to the inferno. Someone has to crawl inside, You enter through the access door. The cylinder stretches ahead, 60 feet of dark, curved tunnel. Every surface radiates heat. Touch the wrong spot and skin blisters. You're carrying fire brick, refractory cement, tools. You need to find the damaged section, clean it, patch it before the kiln heats up again. The air is bad. Residual gas, dust, carbon monoxide. You're breathing particulates that coat your lungs, and you're alone in a steel cylinder that could be activated at any moment because the lockout-tagout procedures we have now didn't exist, because automated systems didn't have manual overrides. Because if someone made a mistake, if someone started the system without knowing you were inside, the doors would seal and the temperature would climb, and there would be no way out. Could you imagine crawling into one of these? But there was another danger, one that killed slowly, one that operators didn't even recognize as a threat, and this one didn't need a malfunction, it didn't need an explosion, it just needed you to show up every day and breathe. Every rotary kiln produces dust, it's unavoidable. The raw material grinds against the refractory. Clinker breaks apart. Coal burns incomplete. Fine particulate fills the air around the kiln. The dust is calcium silicate, fine as talcum powder, light enough to float in air for hours. And when you breathe it in, it doesn't come back out. It embeds in the tissue of your lungs, deep in the alveoli, the tiny air sacs where oxygen crosses into your bloodstream. The dust sits there. Your body tries to seal it off. But silica dust is insoluble. It can't be broken down, so the body does the only thing it can. It builds scar tissue around it, one particle, one scar, microscopic, invisible. But a man working in a cement plant breathes thousands of particles every hour, every day, every month, every year. The scar tissue accumulates, slowly, silently. The lungs stiffen, the air capacity shrinks. Now breathing becomes harder, then labored, then impossible. The disease is called silicosis, and in the early cement industry, it was epidemic. Workers didn't know what was happening to them. Not at first. Silicosis takes years to develop, sometimes 5, sometimes 10, sometimes 20. A man might work in a cement plant for a decade before he noticed he was winded climbing stairs. By the time he couldn't breathe without gasping, the damage was done. Irreversible, fatal. Men called it the stone dust disease. They knew it existed. They saw colleagues wither. They watched men who'd worked the grinding houses for 15 years struggle to walk across a room without stopping to catch their breath. But there was no diagnosis, no formal name in medical literature that connected the symptoms to the workplace. Doctors called it chronic bronchitis, pneumonia, sometimes tuberculosis. Silicosis makes the lungs vulnerable to TB, and the two diseases were so often found together that for decades no one separated them. The dust was everywhere. It was just part of the job. Men coughed, men got sick, men died younger than they should have, but no one was studying the air they were breathing. No one was tracking the pattern. It wasn't until the 1920s and 1930s that industrial hygienists began to understand what silica dust was doing to the human body, and even then the cement industry resisted the findings. A rotary lime kiln was being started after a shutdown, standard procedure, but air had remained inside. It mixed with gas in ratios no one was monitoring. When the burner was lit, the entire kiln exploded. 7 people died instantly. Many more were injured. The damage exceeded $3 million. The cause, incomplete combustion, dust buildup, air that should have been purged but wasn't. According to safety engineers, such explosions are not uncommon. Think about that phrase. Not uncommon. This isn't a freak accident. This is a design characteristic. The rotary kiln, by its nature, creates conditions for catastrophic failure. Explosive fuel mixtures, thermal stress beyond material limits, confined spaces filled with toxic gas. Every single one of these kilns was and still is a potential bomb. And yet by 1905, these machines were everywhere. By 1910, there were over 300 rotary kilns operating across the United States. New plants were going up every month, and every new kiln meant new operators. Men hired off the street, handed tools, pointed at a 60-foot cylinder of fire, or told to keep it running. Here's what we know. In the early 1920s, the Bureau of Labor Statistics estimated 30,000 workplace fatalities per year across all American industries. Since then, about 1 million workers have been killed on the job. How many of those were kiln operators? How many were maintenance workers crawling inside cylinders? How many were technicians lighting burners? How many were men whose lungs filled with dust over the course of a decade, who coughed their way to an early grave from a disease no one bothered to name until decades later? We don't know because the bodies weren't counted separately. The deaths weren't tracked by machine type. The cement industry didn't publish casualty reports. When a man died of silicosis in 1910, it was recorded as pneumonia. When a man was burned by blowback, it was recorded as an industrial accident. No mention of the kiln, no mention of the fuel-air mixture, no record that would let anyone see the pattern. The rotary kiln didn't get replaced, it's still here. Right now, over 95% of the world's cement comes from rotary kilns. The same basic design: steel cylinder, refractory lining, rotation, fuel at one end, material at the other. The kilns got bigger, 6 meters across, 230 meters long. They produced 10,000 tons per day instead of 125 barrels. The technology got more sophisticated: computer controls, infrared monitoring. But the core principle hasn't changed because no one has invented anything better. Cement making requires temperatures that destroy materials. It requires continuous processing. The rotary kiln is still the only machine that can do all of that. So the beast that killed men in the 1890s is still running. Safer now, yes, better understood, better maintained, but still dangerous, still capable of exploding, still requiring someone somewhere to crawl inside a hot cylinder and patch the lining. Every concrete building you see, every highway, every bridge. The cement came from a rotary kiln, the Panama Canal. 62 miles of waterway carved through a mountain range. The concrete that lined those locks, that sealed those chambers. Rotary kilns cement millions of barrels. Without the rotary kiln, there was no way to produce cement fast enough, cheap enough, in the volumes the canal demanded. The Hoover Dam, a wall of concrete across the Colorado River, taller than a 30-story building. 3 million cubic yards of concrete. The concrete that holds it together, that bears the weight of an entire reservoir. Rotary kiln cement. Only the rotary kiln could produce cement in those volumes on that schedule. The skyscrapers of New York, Chicago, Shanghai, the interstate highway system. 40,000 miles of paved road, all of it. This machine that men fought to keep alive in the 1890s built the modern world, and we don't even know it exists. What did the Americans figure out that the British missed? It wasn't one thing, it was several. Better fuel, the protective clinker coating on refractory, longer kiln lengths. But more than that, it was willingness. Willingness to accept the danger. Willingness to keep running kilns even when the refractory was failing. Willingness to send men inside hot cylinders. Willingness to bury the dead and keep producing. The British saw Ransom's failures and gave up. The Americans saw the same failures and pushed through. Not because they were braver, not because they were smarter, because they had no choice. American labor was expensive. European cement was cheap. The only way to compete was to make the rotary kiln work no matter what it cost. And it cost plenty. Remember Alonzo Navarro? Here's what he saw that convinced him. And he saw a machine that could run continuously, and a machine that, for all its failures, for all the brick that crumbled, it never stopped. It kept turning. That was the insight. Not that the kiln worked perfectly. It didn't. It failed constantly, but it failed forward. Every rotation was another chance. The machine was a learning engine, ugly, violent, destructive, but it never gave up. That's the legacy of the rotary kiln. It transformed civilization. It enabled the construction age. It made cheap cement possible, and it did it through brute force by accepting that materials would fail, men would die, and the only path forward was keeping the fire burning regardless. The early cement makers weren't trying to build a perfect machine. They were trying to build one that worked. Safety was secondary. Worker protection was afterthought. They built the beast first. They learned to control it second. And even now, more than a century later, we're still learning. Because the rotary kiln is still failing, still warping, still exploding when procedures aren't followed. The difference is we count the bodies now. We investigate the failures. We write regulations. But the machine itself hasn't changed. And until someone invents a fundamentally different way to make cement at industrial scale, which no one has in 135 years, it won't. The beast is still out there, still spinning, still burning at 2,600 degrees, still building the world, still demanding its price. Only now we know exactly what we're paying.